Okay. So, Gibbs free energy, or change in Gibbs free energy of a reaction, has this relationship with enthalpy and entropy that we've been talking about. And you told me if delta G is negative, then it's spontaneous. Okay. So actually, we can use that, use this relationship to come up with an estimated temperature that the reaction will be spontaneous, kind of the tipping point. And so what you do is, let's see if I have it here, yeah. What you do basically is set delta G to 0 and then solve for temperature. So it looks like, do I have it here? So if we set this to 0, okay, and then what that gives you, negative delta H Rxn is equal to negative T delta S Rxn. Oops, yeah. And solving for T then, T is just a ratio of delta H Rxn to delta S Rxn.
So I was confused because with the knot, I'm assuming, well, it's 25 degrees, but those numbers are at 25 degrees. The whole thing isn't necessarily.
Right, exactly.
Okay.
Exactly.
Okay.
So this is kind of a review slide a little bit. Spontaneity occurs when delta G is negative, so the reaction goes that way, okay? If delta G is positive, the reaction is not spontaneous. If delta G is equal to 0, then the thing is kind of a stalemate. It might be going forward and going reverse, but the rates are equal, so it's at equilibrium. So now I thought to kind of put this in perspective, I would remind you of equilibrium constant expressions. So here we go. A plus B in equilibrium with C and D. And we said you can come up with Kc is equal to molar concentration of C, molar concentration of D, divided by molar concentration of A, molar concentration of B, right?
Mm-hmm.
Cool. So, and this is, let's see, this is a constant. But we also said that there is this thing called a reaction quotient, and that is a snapshot. Right?
Mm-hmm.
So their concentrations aren't necessarily at equal. Right, okay, good. Just to kind of remind you how that goes. Now, let's kind of relate delta G and K. I'll show you what this looks like. Okay. So we said if our snapshot, I'm not going to redo it because it's on the slide, but if your snapshot is equal to your constant, then it's at equilibrium. Okay. Well, that's kind of analogous to, we said, if delta G is equal to 0, it's also at equilibrium. There's a connection here. We said that if your Q is too small, if your reaction quotient is too small, then that means that you don't have enough products. If it's too small, then it's going to go in the forward direction, didn't we? The forward direction is spontaneous. Okay? So that actually corresponds to a negative delta G. One more thing. We said if your reaction quotient is too large, then that means you have too much products and it actually needs to proceed back to the reactants. Wait, yeah, back to the reactants. And that's a non-spontaneous sort of deal. And that actually corresponds to a positive Gibbs free energy, change in Gibbs free energy. Okay? So I'm not necessarily going to show the derivation, but as it turns out, there is an important relationship between, for a system at equilibrium, between Q, K, and G. So remember, that's the proportionality symbol. As it turns out, the Gibbs free energy of a reaction is proportional to the natural log of the ratio of the reaction quotient Q to its equilibrium constant K. Well, we know that we can replace proportionality symbols with equal signs. And so again, without showing you the derivation, and I'm trying to see, is this one on here? Yep. Without showing you the derivation, here is the link between Gibbs free energy, the change in Gibbs free energy of a reaction, and the equilibrium constant, K, at some temperature T, and of course R is the ideal gas law constant. So I'll show you how we can use that in problems, or in a problem. Now, one of the things, this might be like you, because I figure equilibrium constant, KCs, have to do with chemical equilibria, okay? This right here is not a chemical equilibrium, okay? And so that gets a little bit confusing. But just for now, if you want to, and this might make sense more in a minute, let's go ahead and I'm going to draw a reverse arrow under that forward arrow, just for kicks. Because to me, that's kind of how I have to think of this sort of problem. I don't know if it's just me or not. But let's just say this is the combustion of methane. Let's just say that you burn methane, okay, and it goes to form carbon dioxide and water. Well, let's just say we can take random carbon dioxide and water and make methane and oxygen out of them. Interesting idea, okay, just for now. Well, earlier when we looked at burning methane like this, we did the thermodynamic calculations, and we came up with delta G is negative 817.9 kilojoules, according to that balanced chemical equation. So it's clearly spontaneous, got a negative delta G. Okay. Well, we're going to go ahead and use this as an example to knock out K. Let's come up with K or Kc for the combustion of methane. It's pretty weird. It is very weird. So we know that this G, this Gibbs free energy of the reaction, is equal to negative RT, the natural log of K, whatever that rate law constant, or excuse me, not rate law constant, sorry, equilibrium constant would be. And so this is the first semester I've really kind of chased this down in my own mind, because so what we're talking about, just to make sure we're all both on the same page, okay? So Kc is equal to the molar concentration of the products, CO2 raised to the first power. So we don't include the water because it's liquid. And then in the denominator, we have the molar concentration of CH4 raised to the first power times molar concentration of O2 squared. So that's what we're talking about. We're going to actually knock out a value for Kc. Well, if we rearrange this, and we've talked about how natural logs are a pain in the butt. They really are. I'm sorry, but they really are. And they're trying to get to that K. We can just begin with, and I'm going to fix it at the end, so just bear with me. I'm going to keep it as natural log of K for now. And we're going to plug in the Gibbs free energy and RT for those. Okay. So Gibbs free energy, negative 817.9 kilojoules per mole. In the denominator, we have R, which is 0.00831 kilojoules per mole Kelvin. And the temperature, we're going to go with 25 degrees Celsius, which is 298 Kelvin. So rounded to three significant figures. Now, this isn't K, this is the natural log of K. We still have to fix the natural log part of it. So round to three significant figures. Looks like kilojoules and moles cancel and kelvins cancel. Whew, the whole darn things cancel, unit-wise. And we're left with the value, three significant figures of 330. That's our ln of K. So we're close. So to get to K, basically what we're going to do, you're going to see on the next slide, we're going to take E raised to the ln of K is equal to E raised to the 330th power. Now, of course, E of ln of k is equal to, so we get k is equal to E raised to the 330th power. So here we go. E raised to the 330th power. Three significant figures, you get 2.08 times 10 to the 143rd. When was the last time you had a number,
Well,
I know, that had, okay, 10 raised to the 143rd power?
I don't remember how to, I guess I could look at it.
What's that?
I don't remember how to do
Put it in your
the-
calculator?
Yeah. but
Yeah, I
I'm
think
like-
there's an E with an
Is there?
X. Right, E, and then there's a little X here, superscript. Yep, that's it. And what did we say about humongous K values? Okay, so humongous K values mean
Oh, there's more product.
there's a lot of product, a lot more product than there is reactant. So when you go back to the, you know, methane combining with oxygen to form carbon dioxide and water, you're like, dude, that thing goes in the forward direction. It does not, you know,
Okay.
favor the reverse at all. So that's that. And let's take a look at these. This will be the last assignment slide, but we are going to take 10 minutes or so and kind of go into the next part. It switches gears, you'll like.
So this is the last assignment slide for today.
Like, that's all right. The last assignment like today. I know. But you could probably coast on homework, probably. Other than sometimes doing makes it sink in. So this is 36. Calculate the K and gives free energy. Now, what I wish they'd done, if you read this, basically you have to do it opposite. First you come up with G, and then you can knock out K. It says when K and G, so G and K. So these are very similar. Let's just do one of these for normal credit. I think they're very similar. So you have to use the values from Appendix D to come up with your delta H and your delta S. Oops, sorry. And then you use that fourth equation to come up with your delta G. Come back here. And then once you have your delta G, it's like we did with this problem here with the methane. You're going to backtrack to get K using that fifth equation. Does that make sense? Sort of. Let me double check. You're evil. Yep. So you'll get delta G from delta S and delta H. And then you're going to go ahead and use the delta G is equal to negative RT ln of K to get to K. And over here in the margin in the green, I kind of reminded you what we just did. Trying to see if this was any better. If this is better, we could do this one instead of that. You get a pick, whichever one you want to do.
Okay.
We'll just do one of them.
But they're both about the same.
Well, this one might be easier because I think this one you only have to use the summation thing once. Once you get G, then you're ready to go ahead and knock it in to go for K. So the thing that's throwing me off a little bit is it's KP, not KC. But as long as Appendix D has KP instead of KC values, so I don't know. That might be harder because remember you can go from KC to KP. So I don't know. Okay.